Everybody, it's Mrs. Dinkelman, and we're in Unit 9, the Differential Equations unit. And this section is talking about two different visuals for differential equations. So one we have done before in AB, which is the slope fields. So we'll review that really quick. And then the new one for BC is Euler's method. So both of these basically are helpful if there's a differential equation that we either don't know how to solve yet, but we still want to work with it, or there's no method for solving it. So there is a whole class in college that you can take called differential equations where you'll learn different techniques for finding solutions. But for now, we're either going to have separable or we're going to have these visuals to look at what the original equation might generally look like. So for slope fields, again, many of you might remember how to do that. What we're going to do is we're just going to put a little small dash wherever with the slope of wherever we're looking at. So this first one, dy dx equals x. For instance, all along here where x is 0, we know the slope is 0. So we're just going to draw a little dash or a little line segment that has slope 0. Now, just kind of a by the way, this is a differential equation we should know. It's really going to be like an x squared over 2 plus c. So we know that our curve should look like parabolas, but it's just nice to actually see a visual so we can see those happening. So here when x is 1, all of these are going to be 1s. And then here at 2, it's going to get a little steeper. And generally on the AP exam, they don't like go and measure and make sure that they're exactly at 2. They just want you to get the idea that they're getting a little bit steeper here. So a lot of times they'll check the zeros to make sure you have the zeros right, and then generally like if they're a positive or negative slope. So I'm going to just do this last one here. I think we're getting the idea. That these generally look like a parabola. So that's the really cool thing about a slope field is even though we're graphing the slopes, what we end up kind of seeing in almost a connect the dot way is that these things are parabola. So we can kind of do what's called swim through the curve a little bit, swim through that current. In fact, a lot of times if you see a map of a river and you want to know its currents, you'll see those little slope fields or direction fields in there. So think about swimming through the curve if you have to do that. So this one, example 2, we don't really know what the original function is going to look like because we can't solve for it. It's not something we can do off the top of our head. Sometimes on these ones, what I like to do is keep track of the slope by doing some sort of chart, almost like a t-chart, but just add an extra column for anywhere you would need to keep track because it seems like a lot to keep track of. So you can kind of do this and then just pick a point like right here. That's when x is 1 and y is 0, and so our slope would be 1. So feel free to use that if you want. A lot of these have patterns in them, so it's kind of helpful to know, like for instance, anywhere x and y are equal, we're going to get a 0. So at 1, 1, and 2, 2, and 3, 3, we'll get 0 slopes. So it's kind of nice to be able to find those. And a lot of times these are like matching on the AP exam or they're on the free response. But the matching ones are kind of nice because you can look for those 0 slopes. Okay, let's keep going here. So this would be, one of my boys' friends is here. Let's just kind of keep track here. So this is going to be at 2, 1. And so that should be 1. And I think all of these are going to be 1s because this would be 0 minus negative 1. Again, so we're just going to kind of keep track of patterns. So let's see here, when we have x is 2 but y is 0, we're going to get 2 for the slope. So these are going to get a little steeper here. This is going to be 3 minus 1, and so on. A little steeper here. I won't do too many of these because I know you can just watch me. Let's look up here. So this is going to be 1, 2. So that's going to turn to negative 1. So that's what's going to happen at these, negative 1s. Okay, you get the idea hopefully there. We can do some more if you want. This example 3 wants us to try to do the curve that's through 0, 2. So I guess I better do at least a little bit more here. So at 0, 2, these get a little steeper. Oops, but negative. I have those backwards, so make sure we have those going the right direction. And then these are going to get even more steep as we go along. so on. Okay, so now let's try to do the solution curve through 0, 2. I was hoping it'd be a different color, maybe in a second. Okay, there's that point right there. So what it kind of seems like we do is we level out here, and then we kind of go up, perhaps, and then go up like this. Sometimes that little leveling out can be an asymptote, so we can see those there sometimes. Generally, they don't give us ones that are too terribly tricky for those. So what I would recommend doing right now is just stopping and doing the slope fields, and then we can get to Euler's method here in just a minute. I'm going to skip over Euler's method graphing by hand activity. We'll kind of do a graphing by hand here in a second, but this is something I would do in class, so I'm going to skip down to actually doing a problem with Euler's method. Okay, for Euler's method, what I like for students to do, and there's other ways to do it, and you'll see books do it a little bit differently, but I really like having this table for organizing what's going on with Euler's method. So you can see there the table that I create. Those are the labels for each of the columns. One thing I'll mention here is I normally just label this last one as dy, but I've also put in there how we calculate what dy is. Think of dy as the change in y, or delta y, which is why it has that little d there. So we can figure out what's happening with the y coordinate from one row to the next by looking at dy. So to me, the easiest way to describe what's happening here is just to go ahead and do an example. And then I'm actually going to draw what's happening for you. I'll do that in the above, on the graph above, just so that you can see the visual. Even though on the AP exam, generally they don't care about the visual, I think we kind of lose out by not seeing it. So I would like to share that with you as well. So I'm going to go ahead and do my table here. Okay, so this n just keeps a track of how many steps. So sometimes they'll say something like do Euler's method with 3 steps. And so you'll know you have to always start with like a 0 step and then go to when n is 3. This one's a little bit different. It just says starts when y is 0, or y of 0 is 1. And it wants us to get to x is 2. And I guess I need to put in here how far we're, so normally it says in here where we need to go. So I'm just going to add that in really quick. Let's do step size 1. We'll just say this. Do Euler's method using 2 steps of equal size. Starting, I don't have to erase all that. Starting with y of 0 equals 1 and to approximate the differential equation for them. They do need to give us some information about either how many steps or where they want me to start and end. Okay. So there's my columns. Okay. So we're going to start with that 0, 1. Like I said earlier, we're going to end at 2, and it wants 2 steps. So I know what's going to happen here is I'm going to have to make sure that my x, just like delta x in those Riemann sums, is an equal increment. And so here really the delta x or the dx is 1. Sometimes this is called the step size as well. Okay, so now with these 2 points, 0 and 1, if I calculate the dy dx, so in this case the y doesn't matter, but in some derivatives or differential equations it does. So that's going to be 0. Remember that dy is always the dy dx times dx, because technically what happens is that, and our dx in this case is 1. So I know that's just 0 times 1, but I'm going to continue to write it 0. So that means the change in y from this row to the next should be 0. Okay, so now dy dx is 2 because we have a 1 here in this row, and so dy dx times our step size is 2. So now the change in y is 2, so then it's a positive 2, which means this is going to be a 3. So the only thing AP really wants is this, and they really want, I learned this last year, they really want you to say y of 2 is approximately 3. That's what they want us to say. Okay, again, we kind of know what the antiderivative of this. It's x squared plus c. Looking at where our start is, this is really an x squared plus 1. So if we go ahead and jot down those points, I'll just use it right here because it's really not that bad. So if we start with 0, 1, and then let's see, the next one is 1, 1. I'm just going to exaggerate just a little bit. And then 2 is at 3, 2, 3. So this is really meant to be like a connect the dot thing. So we would connect these two with a line segment, and we would connect these two with a line segment, and we're starting to get the idea of what the shape of it is. Again, we know it should be a parabola, just like when you're a kid and you do those connect the dots, if you make them really angular, you can kind of see those, but if you kind of get the idea that, oh, maybe this should be curved, then you know the shape of this particular function. So if we had smaller step sizes, we'd have more little line segments, and that would help us get out what the actual picture is going to look like. So connect the dot. Again, AP just wants this ending answer here. Okay, so now you should be able to get to those Euler method problems. Again, some of those I've already set up the table for you, just kind of slowly releasing that and letting you set up the table for, I think, the very last one there.